Hi, we're going to talk about vibrational spectroscopy. Before we do that, I just wanted to answer a question I had when we were doing rotational. Camera going. So remember when we were looking at rotational spectroscopy in the last lecture, I couldn't remember why delta K had to equal 0. So delta J, which is the angular momentum of the molecule, has to either go up 1 or down 1. So if it's absorption spectroscopy, it'll go up 1. If it's emission spectroscopy, it'll go down 1. And then delta K has to equal 0. So remember, delta K is the quantum number for the rotation about the symmetry axis. So if you had something like nitrogen or ammonia, it would be the axis of rotation where the axis things are rotating around goes right straight through the nitrogen, and then the 3 hydrogens rotate around that axis. And if you think about it, that means that the dipole moment isn't changing with rotation. And so with that symmetry axis, which it was called the I parallel, the moment of inertia for that particular axis of rotation, the dipole moment doesn't change with rotation, then you're not going to be able to absorb a photon in order to do that. So you can carry, or you can change the total J of the molecule because you have the other 2 axes of rotation, but not that one about the symmetric axis. So now we're just going to go on and talk about vibrational spectroscopy. So this is section 11C. And we're going to use most of the time the harmonic oscillator model, and we'll see why in just a second. It's valid. It's not perfect, but it's perfect, or it's pretty perfect for ground state vibrational states. So you may have to go and follow along in the book in order to see this more clearly. So the potential energy function that we're going to use is this one right here. This is the harmonic oscillator potential energy function, where X is, let's say if we have HCl rotating or vibrating, we have some distance where it's at equilibrium. And so X equals the bond length we're at minus that equilibrium bond distance. So it's how far away you are from equilibrium. So when we solved this problem back in chapter 8, we know the energies for it. So what we want to think about is this parabola here is the black line. And it shows you that if you squish HCl too close together, the nuclei start to interact and you get repulsion. When you're at the bottom of the well, you're at the perfect internuclear separation, and so that's called Re. And then as you go to bigger X values, the HCl is stretching apart from each other. So the parabola model wouldn't allow the bond to break. So we'll see when we talk about anharmonicity how we need to add some other terms to our potential energy essentially to make it fit molecules better. So the energy, so vibrational spectroscopy, adding energy to make a molecule vibrate at a higher level is usually in the IR region. So the photon of IR light tends to have the right energy to excite vibrational states. Remember, it was microwaves, photons that excited rotations. So here's our harmonic oscillator. These are the energies that we had from focus 8. So the energy of a vibrational state is a quantum number V plus 1/2 times h nu. And V can be 0, 1, or 2. But even when V is 0, there's still vibrational energy. It would be 1/2 h nu. So for that parabola, the energy states are equally separated. The ground one is at 1/2 h nu, and then you go up by h nu each time. Oops. So 1/2 h nu, and then when the quantum number is 1, it'd be 1 plus 1/2 h nu, so 3 halves. When it's 2, be 5 h nu. So it's a uniform ladder of all energies of equal separation. And if you know the frequency, which you can figure out by knowing the energies, then you can figure out something about the mass of the particles, as well as the force constant, so how hard it is to move that bond. Oftentimes we work in units of reciprocal centimeters, and so when we change these to wave numbers, then we just have to put a C in there, because nu over C equals wave number, so C times wave number equals nu. So you'll oftentimes see these units, same exact value for energy, just starting with a different set of units. So if we look at self-test C.1, just asks us to get, it gives us the vibrational frequency of HCl. And it asks us what's the force constant of the bond. So this is on page 469. So we have the mass of chlorine. So we have, I must have given this the isotope. Yeah, so it's the molecule that's vibrating is a diatomic chlorine molecule where both of the isotopes are the Cl35. So to get the effective mass, it's mass of A times mass of B over the sum of the two. So this effective mass is given in equation 2C. And the effective mass really takes into account what's really moving. So if you have two particles that have equal mass, they're each moving relative to each other. And what we find is then the effective mass is 1/2 times the mass of either one of them, based on this effective mass equation. Oops, I put it right here, so there it is too. So when I plug this in, my frequency they gave me, all I have to do is solve for Kf, the force constant. If I do everything in SI units, I end up with 329 newtons per meter for the force constant. So when we think about vibrational transitions, in order for them to occur as a result of absorption or emission of a photon, the electric dipole moment of the molecule must change during the vibration. So sometimes that means the molecule has to have a permanent dipole, but not always, we'll see. But it's just like with rotation, in order for a photon to interact with the molecule, you have to see a changing electric field, because the photon is a wave with a oscillating electric field. So you have to have a dipole moment that changes throughout the process. So let's go to WebMo really quickly. So I'll stop that share. And I think I can leave that on. Then I will go here. Okay, then I'll share it again. Sorry. Changing screens on here is a little time consuming. So I just want to use WebMo to look at example 11C.1. So we can actually look at those. So it asks us to identify which of the following molecules are infrared active. Gives you diatomic nitrogen. When you think about diatomic nitrogen, the answer has to be no. It doesn't have a dipole, and as it stretches, it only has that one mode. It can't change dipole moment either. So, but let's look at CO2, because CO2 is a linear molecule. And so it doesn't have a dipole moment, but some of the modes of vibration are infrared active. So let's just create CO2. simple calculation. I'm going to do optimize it and then do the vibrational frequencies. Hopefully in WebMo you only have a minute because it's free. So if your calculation takes longer than a minute, you'll have to maybe do it in steps, like optimize it first. But that didn't take long. So let's just look at these frequencies, the modes of vibration. So when you go down here, gives you rotational constants, but then it gives you the frequencies of the IR spectrum. So let's look at these. Go back. Oh, you have to do this. So now it actually shows you how the molecule is moving. So it's bending essentially. So that is changing the dipole moment. So that would be IR active. So when we look at that, oops, I guess I just go back down here. When we look at that one, it's IR active. There's another one that's also bending. It's just in a different direction. The other one, this one, looks like it's probably IR inactive. Yeah, and this is the symmetric stretch. So if both oxygens are going out and coming back in, you're not changing the dipole moment. So that's not going to be IR active. But this last one, called the asymmetric stretch, where one oxygen is moving out while the other is moving in, that will be IR active. So that just allows you to look and actually make sense out of the fact that the dipole moment has to be changing. So some of the modes are active in CO2, but not all of them. Okay. So if we want to think about when a photon is absorbed or emitted, we want to think about the difference in energy of two states. So in number 4, it's taking the difference in energy of the ground state up to the state up to any other state. So V plus 1/2 going to V plus 3/2 means you're going between any two states. So equation 4 will tell you how the frequency is related to the difference in energy of those two. So that's what you'll be measuring if you do an IR spectrum. And the thing with vibrational energy in general, takes so much energy to excite vibrations that if you have a sample at room temperature, almost every one of your molecules will be starting out at V equals 0. So you don't have any excited states just based on the temperature. So turns out that, start here. Well, first take a minute, stop, and do self-test 11C.3. Just looks at calculating what the wave number is based on that equation I just showed you. So what is the frequency of light in wave numbers that corresponds to this transition? In general, the harmonic oscillator works pretty well as a model because, as we just said, in general, at room temperature, you're starting in the ground state. So we look at this blue being harmonic and this guy being anharmonic, meaning it's not a parabola. It has a different shape. When you're at low vibrational states, these two are going to have about the same solution. So the energy states for this two will be about the same. But as you go up and up, the anharmonic ones get closer and closer until you reach this point, and then the molecule can dissociate, and then they're infinite. They're not discrete anymore. There's a continuum. So you only need to use this equation for anharmonicity when you're in some excited states. So in general, when you're at the bottom of the well, it looks very harmonic. So notice what this allows is that as the molecule stretches further and further, it allows the bond to break. which is a physical property we see of molecules. So this green line makes a lot more sense for molecules. We tend to use the harmonic oscillator approximation because at low V's or low energy states, they match pretty well. So as you go up, this term right here, the anharmonicity, is essentially a measure of the shape of that. So there are ways to measure that with spectroscopy. And if you have that, you'd be able to look at the shape and think about when the molecule will break, do things like calculate the dissociation energy. So that's IR spectroscopy where you're actually absorbing photons, but you can also use Raman spectroscopy to excite states of vibration. And turns out, like we said, that the ground state's the most populated. So Stokes, which is the type of radiation where you're scattering light off the molecule and the molecule is taking some of that energy to go up a state because it was at the V equals 0. So Stokes is going to be the most intense because you really don't start with anything in V equals 1 or anything higher where you could give energy back to the radiation. But Raman spectrum lets you do molecules that you can't necessarily do with absorbing photons in the infrared. So for a Raman transition to occur, the molecule's molecular polarizability must change as the molecule vibrates. So that means polarizability, you might remember from London dispersion forces, is essentially its ability to hang on to its electrons, or how easy it is to distort them. So when you look at that, even a molecule like H2 doesn't have a dipole moment. Dipole moment doesn't change when it stretches, so it's not IR active. But as this gets longer and thinner, the polarizability goes down. So it's it's easier to distort the cloud. So the polarizability does change as the molecule vibrates. So you will be able to study it with Raman spectroscopy. Raman has the same selection rule that the vibrational state can only go up or down by 1. So depending on if you have Stokes or anti-Stokes, you're not going to have a lot of anti-Stokes where it goes down by 1 because it never was up by 1, but same selection rule. So when we talk about things other than diatomics, like we looked at with the CO2, then you can have more than one peak in your spectrum. So you can have peaks for, in that CO2, there were 3 IR active peaks for CO2 and 1 IR inactive. And that's how many vibrational modes you have, but you could get information about the molecule from each of those. So the number of peaks that you're gonna have is, or the number of vibrational modes is related to the molecule. So these equations on page 472, let's start by thinking about linear molecules. So how many vibrational modes does a linear molecule have? Both equations start out with 3 times n, because for each atom in your molecule, there's an x, y, and a z to describe where it is in space. But if you're going to change and use internal coordinates, you're going to talk about what angle it has in spherical polar coordinates, and then what's the distance for all the stretches. Then you're going to subtract from this first 3, just plain 3, not 3n. So 3 of those coordinates can be separated out, and that's just it flying through space. So center of mass moving through space. And then you have to subtract from it the number of coordinates that you use to describe its rotation. And if it's a linear molecule, it can only rotate in 2 different directions. So it's 2. And so you end up with 3n minus 5 for linear molecules. But for nonlinear molecules, the same argument, except you have 3n, 3 coordinates for each atom. The whole molecule can go through space, and it can rotate around 3 different axes. So you end up with 3n minus 6. So if you want to figure out how many possible vibrational modes you have, those are the 2 equations given on page 472 that will allow you to decide how many modes each molecule has. So the rest of the discussion on page 472 is kind of looking at what we already looked at with CO2, how those modes look, what are their actual motions. And just like a diatomic has to change dipole moment as it vibrates, for a normal mode to be infrared active, the motion must give rise to a changing dipole moment. So with CO2, I think I'll go back there because I'm going to go there again anyway. So with our CO2, this mode right here, the dipole moment isn't changing, so that's not going to be IR active. Whereas when you look at the other ones, whoops, why did I look at the same one? Look at a different one. There, and you can rotate this guy. There you can see better looking at it that way, that the dipole moment is changing as the molecule vibrates. So you can distinguish which are going to absorb and which aren't going to absorb by looking at whether or not their dipole moments change. So they want us to identify a normal mode in benzene that's not IR active. So let's see if we can do that quickly. So I'll go back and start a new job. It's much easier to import by name than try to draw a structure and get it even close. Okay, so hopefully it's not too big to do this all in one calculation. Optimize it and do the frequencies, but if it is, we'll have to go back and do it in 2 steps. Oh, it worked. So let's go down and look and try to decide which one of the vibrational frequencies, whoa, yeah, like it said, there are a lot. Well, we can pick out which ones aren't IR active by just which ones have no intensity. So let's see if it's obvious. It's not so obvious. Let's look at another one that has a 0. Let's see if there's a different one. Those are very hard to see, actually, aren't they? Let's look at this very last one. There we go. That one's easy to see, where all the hydrogens are stretching out. So in the process of that motion, the dipole moment shouldn't be changing. So usually you can see things pretty clearly on Webmo with the movies that they make. Okay. So if you do your IR spectroscopy in the gas phase, generally, that is going to allow the molecule not only to absorb a photon to vibrate, but if the molecules aren't held rigid in the liquid or the solid phase, you can also increase their rotational energy in the process. So you get what's called the vibrational rotational spectrum. And at the bottom of this page. We have the equation for that. So each transition is going to change the vibrational energy, and it's going to change the rotational energy. So these are the energies that we used for the harmonic oscillator. We're going to add to that the rigid rotor energies. So the equation is approximate because we know you have to make a correction for anharmonicity, and you also have to make a correction for centrifugal distortion. But to a first approximation, that's the equation that would tell you the energies. Your selection rules are that these aren't the selection rules, these are just where the locations will be. So this first one says you can change the vibrational energy because the selection rule said that V has to go up or down by 1. You have to change the rotational state only 1. And if you do, you can also change the rotational state by 1. When you do that, if you change it by -1, your frequency will be less, so you're not absorbing as much energy. So that says you go up vibrational state, but down rotational state energy. So it doesn't go up as high as it would if you were just undergoing a transition between two vibrations. This guy is actually forbidden, this thing called the Q branch, where V goes up by 1. So you have a frequency for vibrational change, but the rotational state doesn't change. That's forbidden from quantum mechanics, so you won't see that branch. And then the other state is where you go up vibrational state and you go up rotational state. And when you look at what that gives you down here, this shows you a picture of what the states all are. And this shows you what your spectrum will look like. You'll have a missing peak in the middle, which would just be the change in vibrational state. And then you have the P branch where you went up vibrational but down rotational, so they're at lower frequency. And then the R branch where you went up vibrational and rotational, so they're above that Q branch in terms of frequency and energy. So stop and do self-test 11C.6 and then come back. And if you have any questions, you can always ask in class. When you think about understanding the vibrations in molecules, Raman and IR tend to complement each other. So for a normal mode to be Raman active, the vibration must be accompanied by a changing polarizability. And it's hard to know then which molecules might be both changing dipole and changing polarizability. So the rule they give you is the exclusion rule states that if a molecule has a center of inversion, which simply means we looked at this with the Girard concept. So we have a molecule, well, let's say like ethene, where if you pass one hydrogen through the center of the molecule, you'll see another hydrogen. So this molecule has center of inversion symmetry, but other molecules like HCl don't, because you pass it through the center and you get a different atom. So that rule allows you to decide. So if the molecule has a center of inversion, then no modes are both infrared and Raman active. So you can use that rule to go ahead and do self-test 11C.7 and just use that. And actually the molecule that they're giving is the one I just showed you, ethene. So should be able to say really clearly whether or not the symmetric stretching mode will be IR, Raman, or both. So check out that one. And that is all for vibrational spectroscopy. We have one more section, which is to look at electronic spectroscopy of molecules. So back in chapter 9, we looked at atomic spectroscopy, so looking at electronic transitions in atoms. But now we'll look at electronic transitions in molecules. And there are some new ideas in there, things like fluorescence, making the laser, all sorts of things that depend on the quantum mechanics of molecules. So that's that.